So let us start today's class with the leakage power dissipation. Before enter into that, let us recap what we studied in the previous class. So in the previous class, we studied about the power dissipation due to charge sharing. Then we studied something about like glitching power dissipation. Then we studied the short circuit power dissipation. So the short circuit power dissipation will happen like when the circuit is in inactive condition, like there will be a short circuit path between the supply rails, between the supply rails in the sense VDD and the VSS. So then we calculated the short circuit power dissipation also. Then we seen about the glitching power dissipation. When the glitching power dissipation will occur in the sense, earlier we might have studied or we might have assumed that all the gates are having the zero delay, but in reality practically but the gates normally will have with some finite delay. Why? Because as you studied in the Cmos, you need to design the circuit with the help of the layout diagram you might have done. But so once you've done the layout diagram, after that with the help of that materials which you used, say example metal 1, metal 2, polysilicon, then N-multi, so many Cmos layers will be there, right? So now once you construct a layout or once you design the layout, after so there is a one the procedure that is called as extraction. That is it will have so many extraction in the sense RC extraction we can call parasitic resistance and capacitance extraction. As the number of parasitic capacitance and resistance increases in the circuit, so there will be a delay. Obviously there will be a delay. That is why I can say in practically the gates will have some finite delay. So further what you need to do, you need to reduce the delay or you need to balance with the circuits. So how we can do the balance in the sense by introducing some buffer circuitry in between. The very important thing is you need not to do the cascading circuits, because if you use the cascading then the glitching power dissipation will occur. So try to avoid the cascade implementation. So possible also to minimize your glitching power. Next we are going to study about leakage power dissipation. So before going to the leakage power, so I need to put some simple concept about the scaling of transistor, or I can say the geometric effect, we can say. The scaling in the sense, may say like a simple, I will say scaling means so increasing the number of transistor in a IC, or simple in simple still I want to say reducing the size of the transistor. That's it. So reducing the size in the sense with respect to the geometry. So what are the which are the geometry or which are the measurements we can able to reduce? If you reduce that, what are the benefits you will get with the help of the scaling? The thing is, I can say like what are the benefits you'll get in the sense if you are doing the scaling, you can able to increase the switching speed of the circuit, then you can able to reduce the chip size, and you can able to reduce the power dissipation. Because when you are going for any design implementation of the circuit, these factors are very very important. But what will happen, the disadvantage in the sense of what will be the demerit of the scaling will happen in the sense like there will be effect will be on silicon dioxide thickness actually, because as you are reducing the length of the channel, that is length or width, so those things again same I can say you have to reduce the SiO2, that is gate oxide thickness, the T oxide. If you are keep on reducing that, so there will be effect. So due to that what will happen, some problem may occur later. We'll study what kind of the problem will occur. Then second thing is there will be a problem will happen the sub threshold current if you do the scaling. Next thing is the sub threshold current will happen for small devices, like in addition to the gate voltage, that is the ground gate to source voltage, we can see the VDS voltage also has greater. Next, I can say there will be a noise problem. So these are the some disadvantages. So to how you can able to do the scaling. So you can do the scaling. You will see this figure here. I'm showing the MOSFET, right? See here, this MOSFET which shows. See here, I can say the scalings are like this. See here, doing the scaling for length of the transistor, then we are going doing the width of the transistor, that is L dash means the new value of L, this is W dash means the new value of W, that S is nothing but the scaling factor actually, or later we may say either we'll use S or A. S or A will use, that is alpha will use, some two factors, these are called as scaling factor actually. Okay, so now simple I can say, if you want to reduce the L new L value, in the sense what will be L dash, so example the L dash will be L, so what you need to do, you need to increase the S, that is the scaling factor. If you increase the scaling factor, automatically the new L value will become less, that is what, same the way you can say ND, that is we can say doping concentration of donor. ND means doping concentration for diffusion actually, so S is a factor. So here substrate doping also, see Na into S. So like this, so many parameters are served. Here we shown only very less. Then you can see the oxide thickness, Tx dash. The Tx dash is equal to Tx by S. See here the Tx, then W, then L, all are inversely proportional to S actually. You might have seen this. Next, the NA, the ND dash, this all are directly proportional to S. So here we need to increase the S. So here we have to decrease the S in the sense, or increase whatever it is based on our requirement, we can do that. Now you can see some standard factors will be there, like standard in the sense, like, let me show. So here I'm showing some standard. You can see this. This is called as constant field scaling. Okay, so here we are having a method called as constant field scaling and a fixed field scaling, constant voltage scaling. One more is constant voltage scaling, the other one is constant field scaling. So now you can see if you are going for channel length, then the scaling factor will be 1 by alpha. That is why there I given as S, right? That is alpha. If it is width means, as I mentioned there, it will be inversely proportional. Then substrate doping means say alpha. Then depletion layer thickness means 1 by alpha is the scaling factor. Then gate delay, that it is 1 by alpha. So like this, various so many scaling factors are there. These are the parameters. So now when you are going for any scaling of your MOSFET, then you need to consider all these parameters. So here I am showing this, the parameters corresponding the parameter. What is the parameter name of your before scaling? After scaling, what is there? See here a constant voltage, as I mentioned, no? Constant voltage scaling. This is full scaling actually. So now you can see here, before scaling the channel length is L, but the after scaling is will be L dash is equal to L by S. So just here I will say the S is nothing but a alpha. You don't get any confusion. Same the way, see W, if it is, then what is the scaling factor is 1 by alpha, that is W by S. You can see this. So like this we can have so many little bit like calculation is there, that is not required actually, just for your purpose, for the information only I am telling this actually. You need to know what is meant by the scaling, how the scaling will be done. So these are the some formulas will be applicable to do the scaling techniques. So now what you do, let us concentrate on the today's session. The today's session, as I mentioned, so we are going for the leakage power dissipation. So when the leakage power dissipation will happen? From the name only I can say the leakage power dissipation. So simple I can say this, when the circuit is, when the leakage circuit means when the circuit is not in an active mode of operation. Mode of operation. So there is a static power dissipation. So this static power dissipation only sometimes we may call as leakage power dissipation. Okay. So now the static power dissipation due to various leakage mechanism. Now we can say simple example the leakage power in the sense simple. We can take in practical reality you can take, consider your laptop example. So what will happen laptop, when you are working laptop, the battery will be charged fully, but you have to think the battery is full. Okay, battery is charged full, but when not in use. You are not in, you are not using your laptop approximately I can say like 6 months example. If I'm not using this laptop for 6 months, what will happen? So the battery is full, but after 6 months, so your battery is dead. What is the reason? The reason behind that is there will be a leakage power. So even though your circuit is not in active mode of operation, then there will be a amount of leakage power will be the slowly the leakage current will, leakage power will be the, due to that your battery will be dead. So you cannot able to use your battery completely. Your battery will be drained. That is this only I said it is a static power dissipation. The static power dissipation will be from direct from the source to the power to VDD to ground. Okay, that is when the circuit is in ideal condition. Okay, now what we'll do, let us say for submicron, for deep submicron. For deep submicron devices, The following leakage currents are become a significant contribution to power dissipation of Cmos circuits. You need to know deep submicron. Which is device is deep submicron? As you know, submicron means simple. You know that already. What is meant by submicron? Example, it is a technology is less than 1 micrometer. That is nothing but a submicron. Means less than a micron technology. Okay. Now the meaning of the deep submicron means what? Less than 250 nanometer. And although as I said, it is approximately I can say example less than 250 nanometer. So as the L reduces keep on. So we are entering into the deep submicron technology. When at this condition, so there will be some significant contributor, some of the parameters will be there that will affect the leakage power, all that will affect the circuit. So let us see the circuit. From that, let's see which are the mechanisms, which are the factors will affect the leakage power dissipation. Okay, now we need to know the leakage power dissipation will happen by three ways, by three components. The one is diode leakage, the second is shift threshold leakage, the third one is gate offset leakage. Okay, now we'll see this is the simple device we said. As you know that this will be your SaO2, this will be your length, correct? This is something what you are. Now you can see so many currents mentioned like I1, I2, I3. And see this I1, I2, and even here also I1, I2, then I3, I4, I5, I6 and I7. So these are the different factors. So this will be bulk. Okay, fine. Now in this current, the diode leakage. The current is simple. I can say I1 and I2 current. This both are the diode leakage. Then subthreshold leakage. So which is the subthreshold leakage here? It is nothing but the I3 is here subthreshold leakage. This one. Next, gate oxide leakage. The gate oxide leakages are I4 and I5. This is the gate oxide leakage because this one, right? This one is nothing but a TX, correct? No? Good. Now let us see each and every term, what it defines. First, let us say the first device is I1. What is the I1 first? The I1 is nothing but here. I1 is nothing but here. Reverse bias PN junction diode leakage current. I1. Next, I2. The I2 is the reversed bias PN junction current, PN junction current due to tunneling of electrons. Tunneling of electrons from the valence band of the P region to the conduction band of the N region. That is I2. Then I3. I3 is a subthreshold leak. I3 is a subthreshold leakage current. What is the meaning of that? So that is nothing but it's between source and drain. Source and drain. When the gate voltage, that is VG, is less than VT. Subthreshold will happen when the gate voltage is less than the threshold voltage. Then it is I4. Then what is I4? I4 is nothing but it is a oxide tunneling current, or I can say it's a gate oxide tunneling current. So what is the meaning of that? It is nothing but this will happen due to reduction in the oxide thickness, that is Tox. That is I4. Then next parameter is I5. So what is the parameters I5? I5 is the gate current. Gate carrier, so not current, gate current. Gate current due to hot carrier, injection of electron. Important is hot carrier. Next, I6. I6 is a gate induced drain loading. That is, I can say gate induced drain lowering. By short, we will call it as GIDL. This will happen, when it will happen, this will happen due to high electric field. High electric field effect in the drain junction. That is I6. Now the last is I7. What's I7? I7 is nothing but it's a channel punch through. We might have studied some of the parameters already in the short channel effects. Short channel, that is the meaning. Okay, when the channel become very short, what will happen? That is in general we have studied. But here we are going to study with respect to the deep submicron devices. Channel punch through current. Punch through current. This will be like a due to the close proximity of the drain and the source in short channel devices. Sometimes in between we may talk about like SCE. SCE is short channel effect. Sometimes we may talk like that also by short form. Now here what we are going to discuss these leakage component. These are the leakage component. So let us discuss one by one now. So first leakage discussion is PN junction reverse biased current. It is the first. Okay. Now what we need to do? Now let us consider the physical structure of Cmos inverter now first. So let me take a physical structure of Cmos inverter. You can see this is the physical structure of Cmos inverter. You can see here, this is the schematic here we shown, right? See here, this is schematic. So let us identify the terminal. This will be your PMOS, this is your NMOS. So simple, I can say this is VDD. Then this terminal is nothing but source terminal. This is the drain terminal. Then this is the drain terminal. This is source terminal. This will be your VSS, V in, V out. Okay. Similarly, one more thing here. The diagram is not given because as you know that the MOSFET always will have 4 terminals. The one more terminal is nothing but the bulk. Correct? That is substrate. So the substrate terminals for PMOS, for always it is connected to source. For NMOS, the substrate always connected to source, that is VDSS. Now we can see that similarly, this will be your physical structure. So here we are having the P substrate. Now we can see this will be your bulk. This is the bulk actually. Okay, similarly even here also bulk. The terminal we can see here, it is source. This is nothing but your drain. Then this will be your drain. This will be your source. Now the same connection we can see here. We can compare these two. Now we can have, this is the P substrate. Here we are having the N substrate. So N well. So N well in the sense we will have N substrate will be there. So substrate is N substrate. Then we'll have the diffusions or P diffusion. It's supposed to be actually we have like P plus and we'll have, sorry, N plus. So if you are having plus, say example N plus like this means it is that is highly doping concentration, meaning high doping concentration. That is the meaning of that. So if you are show anywhere N minus means it is a lightly doped concentration. That only we will see. See now here we show some diodes. Now we can see this will be your N, correct? This is N. You can see in this diagram here the source terminal. This source on this drain we can see P. So P in the sense we are having the diode P, right? It's P diffusion. Okay, P. Then the bottom here N well. N well is means nothing but it's a N substrate. That is a N type. So it is a N type. Okay. Same the way even here also the drain also. So P, that is N. Correct. So this is also P and this is N. But you can see this is a bulk is nothing but what? This is the n substrate, so n, it is connected over there. But for PMOS, this will be your VDD, this will be your VSS. Always will connect the VDD to positive, correct? No, so connected to positive, bulk is connected to positive, means I can say the source drain diffusion and n well diffusion form a parasitic diode. So which is this one, this diode only I can say. This diode is parasitic diode. It will form parasitic diode in the bulk of silicon substrate. You can see internally, if you see, it will form a diode here actually. So here we can see it is a VDD. So this n, right, positive, VDD is positive. Then here it will be bulk is n substrate. It is a n actually. So positive is connected to n substrate. So I can say it is here reverse bias, correct? It's a reverse bias. So we can say the parasitic diodes are reversed bias, then their leakage current, the parasitic diodes are reversed diode. So what I will do, I will make it like I'll give some name also here, like it is, I'll give D1, this I will give as D2. So diode 1 and diode 2, it's a reverse bias in this, right? Reverse bias. So what will happen? Then the leakage current will be contributes to the static power dissipation. So what you will do now? Let us write the their leakage current contribute to static power dissipation. I will write static power is PS, okay, very short. Now let us write the current for one diode, because two diode, current for one diode is given by, that is I can say reverse diode leakage current. So if you see I, okay, reverse diode leakage current. So now what I'm going to do, this I'm going to take as ID, that is diode current straight away, okay, this one. So now let me write the notations actually. IRDLC means reverse diode leakage current. That is, I'm going to take as ID. Now let me write the diode equation, you know, right? For diode current, that is equations. So what is the diode equation current actually? ID is equal to, you might have studied already, IS into e to the power minus QV by KT minus 1. But here let me write the expression which is given like same. It is similar to that. Okay. IRDLC is equal to A into JS e to the power minus QVD divided by NKT minus 1. Now just you have to compare these two. Okay, both are equations, because this is the diode equation. This is the simple ideal diode equation, current equation, diode current equation, which you studied in your PN junction diode. So see, just little bit of the factors we written over here. Now, where the JS or the IS, where IS is nothing but JS here. So if you want to write, you can write like this, where this IS is nothing but A into JS actually. Yes, right? So now let me say what is JS. The JS is nothing but is the reverse saturation current density. Current density. So this will increase the temperature actually. To increase with temperature. Where IS is EJ is. What is VD? Where VD is nothing but, as you know, that it's a diode voltage. What is the N? The small n here. So the small n is nothing but the emission coefficient. Emission coefficient of the diode. So sometimes n will be approximately is equal to 1. That is why here I am not written. Okay, in the top it is not there. What is the Q? The Q is charge. Charge of an electron. So that will be 1.602 into 10 to the power of minus 19 coulomb. Charge, okay. Next, where K is Boltzmann constant. The Boltzmann constant is nothing but 1.38 into 10 to the power of minus 23 joule per Kelvin. Next, where here in the T is nothing but the temperature. This T, capital T is nothing but a temperature actually. But temperature in the sense temperature in Kelvin, but Vt is equal to Kt by Q. Okay. So in the equations and all, see here the top written. This one sometimes if you see in books minus Q Vt will be there. Kt by Q, that is known as thermal voltage actually. That is Vt, no? This Kt by Q is nothing but a thermal voltage. By simple I can say at a room temperature, the thermal voltage will be approximately is equal to 26 millivolt. But apart from changing the room temperature, then your this value will get changed. How you can write in the sense that this T is the this T naught I will say better. So this T naught will be is equal to T plus 270 degree. That's actually we need to do. Okay. Now we take this equation. The leakage current approaches IS, that is the saturation, reverse saturation current. So the reverse saturation current even for a small reverse bias voltage across. So simple I can say even a VD is very small. Example take it. This is very small. What will happen? E to the power a very small value, then it will become as approximately be 0 only. Then I will get ID will be also will be is equal to 0. But I cannot say it is 0 practically. Theoretically only I can say 0. So the reverse saturation current per unit area will be defined as the current density. So now then the resulting current will be approximately the IS is equal to AD into IS. This is what it's supposed to be AI given, right? It is I'll write as AD also. So you need to know what is the AD. Then the AD is nothing but area of diffusion, because the diode is occurred in the diffusion part actually, correct? So area of diffusion. So it will be about how much in the sense 6 micrometer square for 1 micrometer feature size. Okay, 6 micrometer square is for 1 micrometer feature size. 1 micrometer feature size means I can say the channel size. It leads to the leakage current would be about 1 femtoampere, 1 femtoampere per device. So 1 femtoampere in the sense around I can say device at per room temperature, how much the leakage current it leads, it's like a 1 femto ampere. May I know what will be the 1 femto ampere? What is a femto? It is nothing but F is nothing but femto. It will be 10 to the power of minus 18. So you see how much the very small current. So with this what I can say, the reverse, that is IRDLC, the reverse diode leakage current will increase significantly with temperature. So now with this I can say the total static diode leakage current for n devices. For one device is only okay. For n devices is given by equation will be, what is the equation we'll get? The equation will be like I R D L C is equal to summation I is equal to 1 to n I. Correct? Summation of all things that will get. Then what is the total static power dissipation? The total static power dissipation for n devices. For n devices, P is equal to VDD into the summation I is equal to 1 to n into II. So this will be the total. Now you can say like the total due to diode leakage. The total static power dissipation due to diode leakage current. Due to current diode leakage current for 1 million transistor now. Just example. Okay. Just example. The total static power dissipation due to diode leakage current for 1 million transistor. If the transistor is 1 million, then how much? Then simple I can say the P is equal to VDD into summation I is equal to 1 to 1 million is nothing but 10 to the power 6. So here diode leakage ID I'll say, okay, ID. Okay, so ID, this is ID actually. Diode leakage will be approximately will be is equal to 0.01 microfarads. So now there is a small enough to make any significant impact on the power dissipation when the circuit is in the normal mode of operation. However, so some of the particular portion of the chip, so we can say any one chip, so some of the particular portion of the chip will remain standby mode for a considerable period of time, then that component of the power dissipation cannot be ignored. So this is about the PN junction reverse bias current. Next, we'll go for the second mechanism. The second mechanism is band to band tunneling current. Band to band means like I can say valence band to conduction band. Tunneling current. Now let us take the example, or let us take the figure for that especially. You know, you see this. Those are transistors, right? Here, if I say this side, this will be your valence band. This is your conduction band. This is a forbidden energy gap. Okay. Now we can see this will be your bulk here. This point is nothing but bulk, I can say. This will be the point is source or drain. This portion. So now when both N region, both N region and P regions are highly doped. So if it is highly doped in the sun, then there will be a high electric field across to a reverse. So high electric field across the reverse bias PN junction causes a significant current to flow through the junction. In the sense simple, I can say in your MOSFET, if you are reducing the oxide thickness, that is nothing but or I can say this we are talking about a deep submicron. As the length is get reduces, same the way you are thinking like oxide, that is nothing but your TX. Example, you consider TX. Okay, if that TX get reduces small and smaller, very thin, if it is there, automatic, then what will happen? Below that you are having a source and drain also is there. Then what happen? There will be a high electric field will be passed through the reversed biased PN junction, because that is a reverse bias. You think there is a reverse bias when you apply more and more electric field over there. What will happen? There will be some significant amount of current will flow through the junction due to the tunneling of electron. The tunneling of electron will move like from like through the under the gate, no, because TX will be there. Tunneling of electron from the valence band to the, that is valence band will have which region? Will have the P region, valence band P region to the conduction band N region. So that is what the figure here we said. But you can see here this diagram, the voltage drop across. This is the voltage drop. Okay, this is the voltage drop. This voltage drop in this junction, it is more than the band gap. Voltage, which voltage? I mean threshold voltage. I would say voltage is greater than the band gap actually. So the tunneling current will be given as, that is what we can say the band to band tunneling current actually. The tunneling current density is given by, like the tunneling current will be, we will write as JBBB. The expression is A into EVABB by EG, gate electric field, okay, power 1 by 2, then e to the power minus B into EG 3 by 2 to the B. This expression actually it's very difficult. It's just so reason I return straight away and take this expression, or just for tunneling current can see this expression where where A is equal to root of 2m q power 3 divided by 4 pi cube h square, and b is equal to 4 into root of 2m divided by 3 cube h. Actually here the parameter, the m is nothing but effective mass of electron, where E is nothing but a electric field or junction, where Q is a charge and H is reduced Planck constant. Planck constant. So assuming that the electric junction assuming a step junction, or I can say step junction, the electric field at junction is given by, that is E is equal to 2qNA ND into F plus PPI divided by epsilon SI into NA plus ND. Whole thing will become root. But this NA and ND are the doping in the P and the N side. Here NA and ND are doping concentration. Doping concentration in the P and the N side. Okay, so NA is for P side, this is for N side. For next class, we'll study about the subthreshold leakage current. So subthreshold leakage current we will study, and we will study about what are the different factors will affect the subthreshold leakage current.